Welcome to another lecture on the course in 3G and 4G wireless mobile communication systems. In the last lecture, we started our analysis of wireless communication systems with diversity. We said we can have a system in which instead of one receive antenna, we can have L receive antennas. The signals at the L receive antenna received at the L receive antennas can be represented as Y1, Y2, so on up to YL, and at the receiver we can combine those received signals with weights W1, W2, WL as W1 conjugate Y1, W2 conjugate Y2, so on up to WL conjugate YL. We also said that this can be succinctly represented in vector notation as W bar Hermitian times Y bar. This linear combination of the signals, L signals received across the L receive antennas can be represented using vector notation as W bar Hermitian Y bar. And we said we also wanted to derive that or compute that optimal vector W bar which maximizes the SNR at the receiver, and we said that can be derived by maximizing W bar Hermitian H norm square, that is the vector W bar which maximizes W bar Hermitian H bar norm square maximizes the SNR at the receiver. We derived an expression for that W bar, and we said that W bar optimal is H bar, where H bar is the vector of channel coefficients divided by norm H bar. Hence, it is aligned with the channel vector. Essentially, the optimal SNR maximizing vector is nothing but identically equal to the channel fading channel coefficient vector scaled by norm H bar. Hence, it is also known as a maximal ratio combiner since it maximizes the SNR. It is also the spatial matching filter since it is matched to the response of my array of L antennas. We also started with an example where we said I have a system with two receive antennas. The fading coefficient across the first receive antenna is 1 over root 2 plus 1 over root 2 j. Across the second receive antenna is 1 over root 2 minus 1 over root 2 j. In this case, we derived the optimal maximal ratio combiner, and that we said is half plus half j and half minus half j, and we said the optimal combined statistic is given as W bar Hermitian Y bar, which is half minus half j times Y1 plus half j times Y2. This is where we stopped last time. Let me finish the discussion of this example. In this example particularly, we can see that norm H equals 2. For instance, we saw here that norm H equals root 2, hence norm H square equals 2, which means the received SNR after maximal ratio combining equals norm H square P over sigma n square, which in this case is 2 P over sigma n square, since norm H square is 2. All right. So, for this case of the example with two receive antennas, we have derived the optimal maximal ratio combiner, we have derived the maximal ratio combining statistic at the output of the receiver, and we also have derived the SNR at the output of the maximal ratio combining receiver. All right. So, now let us move on to an analysis of the complete analysis of the bit error rate performance of this maximal ratio combining multiple receive antenna receiver. All right. So, we will start our discussion today with an analysis. So, let me give the title of this, that is an analysis of bit error rate of this multiple antenna bit error rate, analysis of the bit error rate of this multiple antenna system. We have seen that the receive SNR equals norm H square p over sigma n square, where norm h square is the norm of the vector of channel coefficients, and this can be written as magnitude h 1 square plus magnitude h 2 square plus magnitude h l square p over sigma n square. That is, the received SNR at the output of the maximal ratio combiner is nothing but magnitude h 1 square plus magnitude h 2 square, so on up to magnitude h l square times p over sigma n square, where each magnitude h I square is the square of the magnitude of the fading coefficient of the ith fading coefficient, which is the fading coefficient between transmit antenna and the ith receive antenna. All right. And this can also be represented as G times p over sigma n squared, where G is the overall gain of the channel, is nothing but summation magnitude h 1 square, magnitude h 2 square, so on up to magnitude h l square. All right. So, I am representing this succinctly as the received SNR as G, where G is the gain of this channel across the multiple receive antennas, times p over sigma n square, that is G is the gain of the channel after the maximal ratio combining process at the receiver. Okay. Now, G, which is equals to norm h square, is a well known random variable with certain properties. Its properties have been studied elaborately in the literature on statistics and mathematics. It has been shown that G equal to norm h square is a chi-squared. It is a chi-squared random variable with 2L degrees of freedom. It has been shown in literature that when each of the fading coefficient is Rayleigh, the magnitude is Rayleigh in nature, that is each h I has a fading coefficient whose real part and imaginary part are Gaussian, and also they are independent, uncorrelated or independent of each other. Hence, when I combine the magnitude squares of L such quantities, the resulting gain G, which is nothing but magnitude h 1 square, magnitude h 2 square, so on up to magnitude h l square, is a chi-squared random variable with 2L degrees of freedom, where L is the number of receive antennas. And because of the time limitation of this course, we will not go elaborately, or we will not go into detail into the properties of this chi-square random variable, but I will just write down the distribution of this chi-square random variable over here. It can be shown that the distribution f g of this gain G of this chi-squared random variable of 2L degrees of freedom is shown to be given as 1 over L minus 1 factorial times G to the power of L minus 1 e to the power of minus G. So, in other words, the distribution of this gain G is f g of G, which is 1 over L minus 1 factorial times G to the power of L minus 1 times e to the power of minus G. Now, why is this essential for us? Remember, similar to the Rayleigh fading channel case, where we looked at the gain A square, we said that the instantaneous bit error rate is a function of A, and then we averaged over the distribution of A, which is nothing but the Rayleigh fading distribution. Similarly, here we are going to look at the instantaneous SNR and average over the distribution of the gain to get the average SNR. And hence, we know that the received SNR, as we have just seen in the previous page, received SNR is G times P over sigma n squared. Hence, the instantaneous bit error rate is nothing but it is q function. Remember, the instantaneous bit error rate is nothing but q function of the square root of SNR. Hence, in this case the instantaneous bit error rate is nothing but q times g of SNR, where SNR is p over sigma n squared. Now, to get the average bit error rate, from this instantaneous bit error rate, I have to average this q of square root g SNR, which is a function of g over the distribution of g. So, the average is simply given as 0 to infinity q of square root of g over g SNR times f of g dg. Look at what I am doing over here. I am taking q square root of g SNR, which is the instantaneous SNR. This is the instantaneous SNR, and I am averaging it over the distribution of g, which is essentially the distribution is a chi-squared distribution with 2L degrees of freedom. All right. So, this is the distribution of the gain g. All right. Now, we will not go into the details of this derivation as we did in the case of a Rayleigh fading channel, because this is slightly more complicated than the previous case, the previous simple case of L equals 1 receive antenna, which is the Rayleigh fading channel. So, I will simply write down the expression over here. The bit error rate with L receive antennas after MRC combining, the bit error rate with L receive antennas after maximal ratio combining, we derived the optimal maximal ratio combiner in the last lecture, is given as, the expression is 1 minus lambda over 2 to the power L times sigma L equals 0 to capital L minus 1, L plus L minus 1 C L 1 plus lambda over 2 to the power L. All right. So, the complete expression for the bit error rate is given as 1 minus lambda whole divided by 2 to the power of capital L, where capital L is the total number of receive antennas, into summation L equals 0 to L minus 1, L plus small l, the index minus 1, choose L. Remember, n choose k or n c k is nothing but n factorial divided by k factorial times n minus k factorial. So, this is capital L plus small l minus 1, choose L, or L plus L minus 1 C L into 1 plus lambda over 2 to the power L, where lambda is defined as, lambda is SNR divided by 2 plus SNR square root. All right. So, we have a closed form expression for the bit error rate of a system with L receive antennas after which employs maximal ratio combining. That expression is given by this summation, where lambda is nothing but SNR divided by 2 plus SNR whole square root. All right. And this is a slightly complicated expression. So, let me simplify this expression progressively. First, let us start with the simple case that we know. Let us start with the L equals 1 case. L equals 1 case, it is fairly simple. It reduces to 1 minus lambda over 2 to the power of L, which is 1. So, it is simply 1 minus lambda over 2 into sigma L equals 0 to capital L minus 1, which is again 1 minus 1, which is 0, times capital L plus small l minus 1, capital L minus 1 is 0. So, this is small l C L, that is L choose L into 1 plus lambda over 2 to the power of L. Now, there is only one term in this expression, which is small l equals 0. So, this reduces to 1 minus lambda over 2 times 0 C 0, that is 0 choose 0 times 1 plus lambda over 2 to the power of 0. This whole term here is 1, which means this reduces to half 1 minus lambda equals half 1 minus SNR divided by 2 plus SNR square root. All right, we said we have an expression for L, any given number of receive antennas capital L. Specifically for capital L equals 1, we derived the expression for bit error rate. So, bit error rate for L equals 1 equals half 1 minus SNR divided by 2 plus SNR square root, and this is nothing but, if you recall, this is nothing but, we saw this expression earlier, this is the bit error rate in a Rayleigh fading wireless channel with a single transmit antenna and single receive antenna. This is bit error rate with single receive. This is the bit error rate of the wireless communication system with a single receive antenna, that is the same expression as we see before. So, we are trying to say that it is consistent with what we derived before in the case of a single receive antenna. Now, let me slightly simplify this for the case of high SNR. Let me simplify for, so let me write down here for high SNR. Now, for high SNR, let us consider the term half into 1 minus lambda, that is half into 1 minus SNR divided by 2 plus SNR square root, which can also be written as half into 1 minus 1 over 1 plus 2 over SNR to the power of half. So, look at this, this is half into 1 minus 1 over 1 plus 2 SNR to the power of half. 1 plus 2 over SNR to the power of half is in the denominator. Now, this as SNR increases, this 2 over SNR term becomes progressively smaller, which means I can approximate this with a first order approximation, and that approximation is nothing but 1 minus 1 plus 2 over SNR to the power of minus half is nothing but 1 minus half times 2 over SNR. So, this is 1 minus half times 2 over SNR, and that is nothing but this ones cancel 1 minus 1. So, the net becomes 1 over 2 SNR. All right. So, half 1 minus lambda for increasing SNR at high values of SNR is approximately equal to 1 over 2 SNR. Similarly, if I compute the approximation half of 1 plus lambda at high SNR, this is approximately half 1. Now, instead of the minus inside, I will have plus 1 minus 1 over SNR. This is equal to half 2 minus 1 over SNR. As SNR increases, 1 over SNR becomes smaller and smaller, hence it is small in comparison to 2, hence this expression becomes half times 2, which is essentially 1. So, we said at high SNR, one minus lambda over 2 approximately equal to 1 over 2 SNR and 1 plus lambda over 2 approximately equal to 1. That is, at high SNR 1 minus lambda over 2 is approximately equal to 1 over 2 SNR and 1 plus lambda by 2 is approximately equal to 1. Okay. Now, substituting this back in the previous expression we had average BER equals 1 minus lambda over 2. Let me write down the complete expression here, times sigma L equals 0 to L minus 1, capital L plus L minus 1 C L 1 plus lambda over 2 to the power of L. Now, 1 plus lambda over 2 is 1, 1 minus lambda over 2 is nothing but 1 over 2 SNR. So, I can write this as 1 over 2 SNR to the power L into sigma L equals 0 to L minus 1 L plus L minus 1 C L or L plus L minus 1, choose L into 1 plus lambda over 2, which is nothing but 1 at high SNR, 1 to the power of L is 1. So, this is simply reduces to the summation L equals 0 to L minus 1 L plus L minus 1 C L, and hence this is 2 L minus 1, choose L, or 2 L minus 1 C L into 1 over 2 to the power of L into 1 over SNR to the power of L. Hence, the final expression for the bit error rate at high SNR, let me write it here, at high SNR, the final expression for bit error rate at high SNR is given as 2 L minus 1 C L times 1 over 2 to the power of L times 1 over SNR to the power of L, where L is nothing but the number of received antennas. So, let me just rewrite that here clearly, bit error rate with L receive antennas after maximal ratio combining at high SNR is equal to L minus 1, choose L 1 over 2 power L 1 over SNR power L. This is the expression for bit error rate with L receive antennas after maximal ratio combining, and of course, you have to remember that it is a high SNR approximation. This is not the exact expression, but this is a high SNR approximation. All right. Okay. So, let us start with here this expression and analyze it further. First, let us do an example to enhance our understanding. So, let us do an example. Let us consider the previous case where L equals 2 receive I am considering the case L equals 2 receive antennas. I want to find out what is the bit error, what is the SNR at which the bit error rate is 10 power minus 6. Remember, in the AWGN case or the digital wired or wireline communication channel case, we did the similar example. We found out the signal to noise power ratio at which the bit error rate is 10 power minus 6. We did a similar example for a wireless communication system with a single receive antenna. We found out that at bit error rate 10 power minus 6, the SNR required is very high. In fact, it is 10,000 times higher than what is required in a wireline communication system. Now, we are trying to do a similar number, compute similarly the SNR required to achieve a bit error rate 10 power minus 6 in a wireless communication system with L equals 2 receive antennas. That is, instead of a single receive antenna, I have L equals 2, that is 2 receive antennas. Now, what is the SNR required? Is it lower? Is it higher? Let us compute that to get an idea. All right. For L equals 2, what is, let me write down the question, what is the SNR required to achieve a bit error rate of 10 power minus 6. What is the bit error rate required to achieve? What is the SNR required to achieve a bit error rate of 10 power minus 6 in this wireless system with 2 receive antennas? From what you have seen previously, the bit error rate at high SNR is 2 L minus 1, choose L, 1 over 2 to the power of L, 1 over SNR to the power of L. Now, L equals 2. So, 2 L minus 1 is 3, choose 2 or 3 C 2 times 1 over 2 square times 1 over SNR square. 3 choose 2 is nothing but 3, 1 over 2 square is nothing but 1 over 4. Hence, this expression for bit error rate becomes 3 over 4, 1 over SNR square, and I want this equal to, that is the bit error rate equal to 10 power minus 6. All right. So, I am saying the bit error rate as a function of SNR is 3 over 4, 1 over SNR square with L equals 2 receive antennas. I want a bit error rate equals 10 power minus 6, hence I am equating this to 10 power minus 6. And now, so I can derive 1 over SNR square equals 4 over 3 into 10 power minus 6, which means SNR equals SNR square equals 3 over 4 into 10 power 6, which means SNR equals square root of 3 over 2 into 10 power 3. All right. SNR square is 3 over 4 into 10 power 6, which means SNR is square root 3 over 2 into 10 power 3. I want to compute the SNR in dB. The SNR in dB is 10 log 10 square root of 3 over 2 into 10 power 3. This can be shown to be, so this SNR required in dB can be shown to be 29.37 dB. So, what have we now computed? We have computed the SNR required to achieve a bit error rate of 10 power minus 6 in a wireless communication system with 2 receive antennas, and we are saying that SNR required is 29.37 dB. If you remember, with one receive antenna, the SNR required with only one antenna was, if you remember, let me refresh your memory, we computed similarly the SNR required with one antenna, we said that was 57 dB. Now, when we added one more receive antenna to the system and we did some intelligent signal processing in terms of maximal ratio combining, that SNR required has come down to approximately 29 dB. So, the reduction is 57 minus 29 dB approximately equal to 28 dB. So, because we have added an extra receive antenna in this wireless communication system, the amount of SNR required to achieve a bit error rate of 10 power minus 6 has come down by 28 dB. Now, let me illustrate to you how significant this is. So, let us say P1 W equals power required with a single receive antenna, P2 W equals power required with 2 RX antenna, then the power required with 2 RX antennas is 28 dB or approximately 30 dB lower than the power required with one receive antenna. Hence, I can write 10 log 10 PW1 divided by PW2 is equal to 28 dB, which is approximately 30 dB, all right, which means PW1 divided by PW2 equals 10 to the power 3, which means PW2 equals PW1 divided by 10 power 3. Look at this, PW2 is the amount of power required with 2 receive antennas at the receiver. PW1 is the amount of power required with 1 receive antenna at the receiver. This is saying with 2 receive antennas, PW2 is PW1 divided by 10 power 3, which is 1000. So, the amount of power required now is 1000 times lower compared to the case when we had only a single receive antenna. So, PW2 is power with 2 antennas and PW1 is nothing but power with 1 antenna. Thus, PW2 is 1000 times lesser than the power required with one antenna. That is, if 10 kilowatts was required with one receive antenna, now we require 10 kilowatts by 1000, which is simply 10 watts. All right. So, adding one more receive antenna has resulted in a significant improvement in the bit error rate at the receiver. Let me summarize our conclusion. Adding one more RX antenna of the wireless system at the wireless receiver has significantly improved bit error rate performance. So, adding one more receive antenna at the receiver in my wireless communication system has significantly improved the bit error rate performance, all right, and hence this scheme receive diversity is a very important technique in 3G, 4G wireless communication systems. Hence, it is very RX diversity is very important in 3G, 4G. RX diversity is a key aspect of receive antenna diversity is a key aspect, or diversity is a key aspect in 3G, 4G wireless communication systems. It is employed in WCDMA, it is employed in HSDPA, it is employed in LTE. Remember, in the first lecture, in the very first lecture, we looked at a list of technologies that are basically categorized or characterized as 3G and 4G technologies, and we said several such technologies are WCDMA, HSDPA, LTE and WiMAX, and all of these techniques use diversity. Here we talked about receive diversity, but there is also a form of transmit diversity which we are going to talk about later. So, all these systems essentially use some form of diversity, because diversity results in a significant decrease in the SNR at the receiver. Alright, hence diversity is a key technology in 3G, 4G wireless communication systems. Hence, we will study this, and this will be a critical component of all the technologies, of the different technologies that we study in this course, which is essentially 3G, 4G wireless communications. So, but let us see why this decrease in bit error rate, or why this significant improvement in efficiency is arising in this system. So, why is this bit error rate decreasing with RX antennas? As I increase the number of receive antennas, we have seen that the bit error rate is decreasing. Why is this decrease arising? Let us look at the expression for L antennas. For L antennas, we said the bit error rate is given as 2L minus 1 CL 1 over 2 to the power of L 1 over SNR to the power of L. Now, for L equals 1, this is simply, as we saw, 1 over 2 to the power of SNR, which is proportional to 1 over SNR. For L equals 1, that is one receive antenna, we have the earlier expression, which is bit error rate equals 1 over 2 SNR, which is proportional to 1 over SNR. Now, when L equals 2, this expression is, as we saw, 3 over 4 times 1 over SNR square, which is proportional to 1 over SNR square. So, look at these two terms here. At L equals 1, at one receive antenna, this is decreasing, bit error rate is decreasing as 1 over SNR. With L equals 2 receive antennas, the bit error rate is decreasing as 1 over SNR square. Remember, at high SNR, SNR square is much larger than SNR, hence 1 over SNR square is much smaller than 1 over SNR. Similarly, for L equals 3, bit error rate equals 1 or is proportional to 1 over SNR cube, which means SNR cube is much larger than SNR square and SNR. So, 1 over SNR cube is much lower than 1 over SNR, hence the bit error rate is much lower with 3 antennas and so on and so forth. So, hence as the number of receive antennas is increasing, as the number of receive antennas increasing, the exponent of SNR in the denominator is increasing, right. So, as number of receive antennas L is increasing, the exponent of SNR in the denominator or the bit error rate is 1 over SNR to the power of L. So, the exponent of 1 over SNR is increasing, hence the bit error rate is decreasing at a much faster rate, is increasing the bit error rate BER decreases at a much faster. As the number of receive antennas is increasing, the bit error rate is decreasing at a much faster rate. let us and let me just show you, to reinforce this idea, let me just show you a plot of the bit error rate of systems with different numbers of transmit antennas. Let me go here. For instance, here I have a plot of the bit error rate of a wireless communication systems with different receive antennas. This blue one here is AWGN, that is the wireline communication system. This black one here corresponds to L equals 1 receive antenna. This red one corresponds to L equals 2. The red dotted one corresponds to L equals 4. The magenta is L equals 8 and the magenta dotted is L equals 20. So, as you can see, as the number of receive antennas keeps increasing progressively, the bit error rate keeps decreasing at a faster and faster rate, and it progressively achieves. Remember, we said for a wireless communication system, the performance is much worse compared to a wire line or a wired communication system. But now, what we see here is that as the number of receive antennas L keeps on increasing, the performance of the wireless communication system progressively improves towards that of a wireline communication system. That is, with as the diversity or as the number of receive antennas keeps increasing, the bit error rate decreases at a faster and faster rate, eventually approaching the bit error rate decrease of that of a wireline communication system. All right. So, let me go back to my lecture here. Let me go back to the lecture slide. So, let us understand why this is arising. So, let us look at this multiple antenna system. Let us look at this multiple antenna system, and let us again ask the question that we asked before: what is the probability of a deep fade in this term? In this multiple antenna system, what is the probability of a deep fade? In this multiple antenna system, what is the probability that the system is in a deep fade? We said that the system model or the receive system model can be expressed as y bar equals h bar x plus n bar. We said the signal power after MRC combining, after maximal ratio combining, is norm h square p over sigma n square, which is also the gain times p over sigma n square. We said that in this system with multiple receive antennas, the received signal to noise power ratio after maximal ratio combining or at the output of the MRC combiner, maximal ratio combiner, is nothing but norm h square p over sigma n squared. Now, the SNR equals norm h square p over sigma n squared, where this is the top one is the signal power, the bottom one sigma n squared is the noise power. And we said the system is in a deep fade when the received power is smaller than the noise power. Remember, in the wireless fading channel case, we said the system is in a deep fade when the destructive interference is such that the received power at the output is smaller than the noise power. All right. So, in this case, the system is in a deep fade when norm h square into p is less than sigma n squared, or g times p is less than sigma n squared, or g is less than 1 over S n r. All right, this system we say is in a deep fade. This system with multiple receive antennas is in a deep fade when the gain G is less than 1 over S n r. All right. Now, we also know that the distribution of this G, that is the probability distribution of this G is G to the power of L minus 1 divided by L minus 1 factorial into e power minus G, all right, which means now I need to find the probability of a deep fade, which is essentially the probability that G is less than 1 over S n r. Hence, that probability is given by integrating this probability density functions between 0 and 1 over S n r, similar to what we did in the Rayleigh fading channel case, and with distribution G power L minus 1 divided by L minus 1 factorial e power minus G d G. So, I am saying the wireless channel with multiple antennas is in a deep fade when G is less than 1 over S n r. That probability can be determined by integrating the probability density functions between the limit 0 and 1 over S n r, and the probability density functions is G power L minus 1 divided by L minus 1 factorial times e power minus G into d G integrated between 0 and 1 over S n r. Now, at high S n r, 1 over S n r is much small, is very small. So, e power minus G is approximately equal to 1, which means this integral is approximately 0 to 1 over S n r G power L minus 1 divided by L minus 1 factorial d G. Now, integral G power L minus 1 is nothing but G power L divided by L. So, this is G power L divided by L, and L times L minus 1 factorial is nothing but L factorial. So, this is G power L divided by L factorial between the limits 0 and 1 over S n r, and this at this point it is the probability of deep fade equals 1 over L factorial 1 over S n r to the power L. Look at this, this is the probability of deep fade in this system, and it is proportional to 1 over S n r to the power of L. This is proportional to 1 over S n r to the power of L. Remember, in the wireless communication system with a single receive antenna, we said the bit error rate is proportional to 1 over S n r, and that is nothing but the probability that that system was in a deep fade. Now, we are saying that in a wireless communication with system with L antennas, the probability of deep fade is 1 over S n r to the power of L. In fact, that is also the bit error rate, that is bit error rate is occurring when this system is in a deep fade, essentially corresponds to when this system is in a deep fade. However, the probability that this system is in a deep fade is now significantly reduced. Look at this, before the probability that the system with one receive antenna was in a deep fade was 1 over S n r. For two antennas, this probability of deep fade will be 1 over S n r square, which is significantly reduced. With 3 antennas, it is proportional to 1 over S n r cube. As you add more and more receive antennas, the probability that this system is in a deep fade decreases progressively. That is what this means. This means with more RX antennas, probability of deep fade decreases significantly. As you keep increasing the number of receive antennas, the probability that your system is in a deep fade keeps decreasing at a very fast rate. Alright. So, the probability that system is in a deep fade decreases with the number of receive antennas, and hence since the probability, since deep fade is what is responsible for bit error in wireless communication systems, the probability of bit error also correspondingly decreases as the number of receive antennas increases. Now, intuitively, why is this happening? What is the intuition? What is the intuition or what is the intuitive reason for this? Let us look at a system with one transmit antenna and one receive antenna. That is, I am saying I have a system with one transmit antenna and one receive antenna. There is only one link. We saw this example earlier. There is only one link between one transmit antenna, one receive antenna. There is only one link. If this link was in a deep fade, then the bit error rate is high, and the probability of deep fade is of this single link is 1 over SNR. 1 over SNR is probability of deep fade. Which is also the bit error rate. We said in a system with one receive antenna and one transmit antenna, there is a single link, and if this link is in deep fade, then the bit error rate is high. The probability with which this single link is in a deep fade is 1 over SNR, hence the bit error rate is 1 over SNR. Now, let us look at what happens when we have multiple receive antennas. When we have multiple receive antennas, and more specifically we have L receive antennas. There are L links in a system with L receive antennas. There are L links between transmit antenna and first receive antenna is link 1, between transmit antenna second receive antenna is link 2, so on and so forth. Between transmit antenna and receive antenna, L is the Lth link. So, with L receive antenna there are L links. Now, even if one of the links, let us say, or two of the links were in a deep fade, then I can use the remaining links to transmit my information, which means for this system to be in a deep fade, all the L links have to be in a deep fade. Alright, because I have L links, for this system to be in a deep fade, all the L links have to be in a deep fade. So, if EI is the event that link I is in a deep fade, what am I looking for? The deep fade, the net deep fade event is P E1 intersection E2 intersection EL. That is, I need all the links to be in a deep fade for this system to be in a deep fade. And remember, all the links are independent, which means P of E1 intersection E2 and intersection EL is P of E1 into P of E2 into P of EL, which is nothing but 1 over SNR. Now, remember, P of E1 is the probability that link 1 is in a deep fade, that is 1 over SNR. P of E2 is nothing but probability link 2 is in a deep fade, that is 1 over SNR. So, I take product of 1 over SNR L, product of 1 over SNR L times, hence the probability of deep fade is now become 1 over SNR to the power of L. We now have another beautiful interpretation, we have a beautiful interpretation of why this system bit error rate is decreasing as 1 over SNR to the power of L. That is, because I have L links, it means for the system now to be in a deep fade or the system to result in disruption of communication, I need all the receive antennas to be in a deep fade. Each receive antenna is in a deep fade with probability 1 over SNR. These events are independent, which means the net probability is 1 over SNR into 1 over SNR into 1 over SNR L times. Hence, the net probability is 1 over SNR power L. This is essentially the deep fade probability, which is decreasing as 1 over SNR to the power of L. Alright. So, we will stop our discussion of this lecture at this point, and we will begin again with a closer examination of this point in the next lecture. Thank you very much for your attention.